Are you someone who loves science and enjoys trying out fun experiments at home? Well, you've come to the right place. Today, we're diving into 14 fascinating surface tension experiments that will definitely amaze you. Hey there, welcome to the Eureka Be Smart channel, and we're kicking things off right now. Experiment number 1, water drop on a coin. In this experiment, we can observe how surface tension forces hold a large water droplet on the surface of a coin. These forces act along the surface of the liquid, striving to minimize its area, as if the liquid is enclosed in a stretchy film that wants to compress its contents. Water droplets naturally try to form a shape close to spherical, and in zero gravity, they become perfectly spherical. Many have probably seen how astronauts in space, where there is no gravity, play with water. It truly floats around in the form of little spheres. In this experiment, I successfully placed an impressive 70 small water droplets on a small coin. Try it yourself and see how many droplets you can place before they all slide off the coin. Experiment number 2, cutting a water droplet with a knife. In this experiment, we're demonstrating a combination of surface tension and wetting phenomena. When the interaction forces between molecules in the liquid are stronger than those between the liquid and the solid surface, the liquid does not wet the surface of the solid, and vice versa. Cutting a water droplet turned out to be quite challenging. I encourage you to try it yourself. Let me know in the comments if you succeed. Hint: the surfaces of the solid and the knife blade should be highly hydrophobic, meaning they repel water. This experiment also explains the saying, like water off a duck's back. For example, waterfowl don't get wet because their feathers are treated with hydrophobic grease secreted by oil glands on their tails. As a result, water beads up and rolls off their feathers. The same principle applies to an umbrella, where water runs off the edges without soaking through the fabric or droplets on the leaves of certain plants. Experiment number 3, needle or pin floating on water. This experiment helps explain why water striders can walk on water. It's possible because the water molecules near the surface have stronger attraction to each other at the phase boundary. That's why water striders can calmly walk on the water surface, while a needle or pin can stay on top without sinking. Take a closer look, and you'll see how the water surface bends, creating support and holding the weight of the object on the surface. Experiment number 4, water stream from a tap. This is a very simple experiment, but it also demonstrates how all systems strive to achieve the most energetically favorable state. In this case, the water stream from a tap always tends to take on a cylindrical shape, which is the most energetically favorable state for the liquid in this scenario. Experiment number 5, soap bubbles. This experiment with soap bubbles essentially demonstrates the same principle as the previous one. Soap bubbles naturally take on a spherical shape, which has the smallest surface area and thus is the most energetically favorable form. In addition to being beautiful, I want to draw your attention to the fact that as long as soap hemispheres are unable to interact with each other, they maintain their hemisphere shape. However, as soon as they have the opportunity to interact and join together as a system, this immediately leads to the system changing its shape to one that is more energetically favorable and has a smaller surface area. Experiment number 6 with wireframes. Soap films always form in a way to minimize their surface area. In this case, using wireframes shaped like a cube and a tetrahedron, it's a perfect demonstration of this principle. Agree, it looks great. Experiment number 7, demonstrating soap water surface tension. This experiment shows the strength of surface tension in soapy water. I took a frame with 3 partitions. When a soap film is stretched across all partitions, the system is balanced and relatively stable. However, if you break the film on one side, the system instantly starts seeking the state with the smallest surface area, which is the most energetically favorable. This causes the partitions where the film was not broken to come together. Notice how quickly and forcefully this happens. The partitions don't even stay in place on the frame. I slowed down the video at these points. Experiment number 8, demonstrating soap-water surface tension on a circular wire frame. This experiment demonstrates the strength of surface tension in soapy water using a circular wire frame. If you lay a wet soap-coated thread loop onto such a film and puncture the film along the thread's boundary, the surface tension forces will stretch the thread to form a perfect circle. This is a quite stable configuration, and such a circle can even freely move around on the surface of the film. Experiment number 9, which demonstrates the change in water surface tension coefficient upon adding a surfactant, surface active substance. I named this experiment Paper Boat with a Soap Engine. If you cut out a boat shape from cardboard or paper like this and place a drop of liquid soap in the cutout on the boat will move due to the change in surface tension forces. In general, adding a surfactant to water reduces the surface tension of water. Experiment number 10, milk dance. Did you know that milk is mostly water? But in this experiment, water isn't the star of the show. It's all about the milk fat, surfactants, and dyes. Add a little bit of dye to the milk, then drop some liquid soap onto the surface, or touch the milk surface with a stick dipped in liquid soap. The surfactant molecules will interact with the fat molecules, causing a lively reaction that the dyes will help demonstrate. Experiment number 11, demonstrating surface tension at the interface of 2 immiscible liquids. This experiment illustrates the fact that surface tension occurs not only at the interface between a liquid and gas phase, but also at the interface between 2 different liquids that do not mix, like water and sunflower oil. When oil is added to water, it forms droplets in a spherical shape and then rises to the top due to differences in density. After the oil stabilizes on the surface, a flattened droplet forms due to gravity. Experiment number 12, colorful and spectacular. This experiment showcases a variety of phenomena and characteristics of liquids. Start by adding dye to water and then pouring sunflower oil on top. After that, drop in an effervescent tablet and you'll witness a captivating spectacle. The carbon dioxide gas produced from the tablet dissolving tries to push through the layer of oil upward, carrying along droplets of colored water that attempt to sink back down once the carbon dioxide gas escapes. Experiment number 13, wettability and surface tension. This experiment involves fire and water, but they play supporting roles. The star here is the chicken egg. When you heat the egg over a candle flame, its surface becomes coated with a layer of carbon, which appears due to incomplete combustion of hydrocarbons. The flame cools upon contact with the egg's surface, halting the combustion process at the carbon release stage, which then settles on the egg's surface. Now, if you lower such an egg into water, the carbon-coated surface of the egg will not wet, and a water film will form around the surface due to surface tension, creating a reflective effect that appears like the egg has a mirrored surface. Experiment number 14, surface tension and density differences. In this experiment, we demonstrate surface tension in liquids and differences in the density of solids and liquids. We start by adding sunflower oil to a glass of water and placing 2 pieces of colored ice made from dyed water into the mixture. Ice has a lower density than water, so it always floats on the surface of the water. However, in this experiment, the density of the ice is slightly less than that of the oil, so the ice cube hangs in the upper part of the oil layer. As the ice melts, it turns into water, which has a higher density than oil. Therefore, the melted water forms a droplet and falls into the lower layer. This process occurs slowly because the water needs to overcome the resistance of displacement forces and surface tension. Please note that the video is presented in a sped-up mode, approximately 15 times faster than real time, to highlight the experiment's key observations.